Okay, so we're going to start this again, sorry. So we were looking at antiderivatives, and I was trying to explain to you that this table only includes sort of the basic functions, that if you're going to take the antiderivative of sine of x, for example, yes, that's negative cosine of x, but you can generalize it so that if you're off by just a constant, now this is only, what I'm talking about right now is only if you're off by a constant. So if you have sine of some constant times x, the antiderivative would be not just negative cosine of that constant x, you'd have this 1 over k to account for the fact that if you took the derivative of this, you'd be multiplying by that k. So again, if you don't follow why the derivative of this expression would give you this expression, you should actually do a little chain rule. Pause the video and do the chain rule. So again, we can generalize that if our function was cosine of some kx, then the antiderivative would be not sine of kx, but 1 over k sine of kx plus a c. And more generally, the antiderivative of e to some constant times x in the same kind of fashion would be 1 over k e to that kx plus c. And in fact, you can even generalize it slightly more. So the point of all these generalizations I'm making is that if the derivative is just something like kx, so here, let me just give you another example. If you're trying to take the antiderivative of e to the 2x plus 1, well, we know the antiderivative would be something of the form e to the 2x plus 1. But when we do a chain rule on this, the derivative of e to the 2x would be 2. So the derivative of this thing would have a times 2 out front, which we don't have. So we can undo that by putting a 1/2 out front. So the antiderivative would be 1/2 times e to the 2x plus 1 plus our constant. And again, you should double check that by actually taking the derivatives. So in all these places where we have an x, we could replace with a kx, and we would have a 1 over k out front. So that's the point I'm trying to make here. Okay, so now you can generalize the rest of the values in those table. And I want to look at some examples of some other notation that we can use for finding antiderivatives. So if you've heard of the class ordinary differential equations, then here are some real basic, simple differential equations where you're given the derivative is some function and you have to solve for the original function. So you're trying to find the solution to this differential equation, means try to find the function y that has the given derivative. So if I start with this, I know if the derivative is 2x plus 1, the original function is the antiderivative. So that's x squared plus 3x plus c. But we're looking for one that we're not looking at all infinitely many curves. We're looking for which ones that when x is -1, y is 0. So notice that if I think about what this function looks like, it's a parabola, and it's the plus c means we've got a whole bunch of them. So we've got sort of this infinite family of them. So we're looking for the particular one that passes through x is -1, y is 0. So like whichever one passes through that particular point. Once you have a particular point, it tells you which curve you're looking for. So how do we find the plus c? Well, we substitute when x is -1. We know y has to be 0. So we just solve for c. So 0 equals -1 squared is 1, minus 3 plus c. This is -2. So when I add it to the other side, I get 2 is c. So the solution to that differential equation is y equals x squared plus 3x plus 2. Right? C is 2. So this is the solution to the differential equation dy dx equals 2x plus 3 with these given values. Okay, let's look at another one. Over here we know that the general antiderivative, so remember this is x to the -2. So we add 1 to the exponent and then divide by the reciprocal, or multiply by the reciprocal out front, sorry, plus 2x plus c, and then we put in the given conditions. So when x is -1, we know y is 3. So 3 equals this reciprocal of -1 minus 2 plus c. So 1 minus 2 is -1. And then we add 1 to both sides, we get c is 4. So our general solution is y equals negative x to the negative 1 plus 2x plus 4. Okay, and now let's just scroll down a little bit more to do this last example. So if I want to solve this differential equation, I know the general antiderivative would be, so the antiderivative cosine is sine of 3x, but then because chain rule, if I took the derivative of this, I'd have a 3 out front, so I want to undo that with a 1/3. And then this is going to be negative cosine of x plus c. So I put in these conditions when y is 2, x is pi, and I solve for c. So 2 equals 1/3 sine of 3 pi. What's that? So sine we know looks like this. So that's at 1 pi, 2 pi, 3 pi. So that's 0 minus cosine of pi. So this one was sine. Cosine looks like that. And at pi, it's down at negative 1. So that's a negative 1. So 2 equals 1 plus c, right, because these are positive. So if I subtract 1 over to the other side, we get 1 is c. So my equation, the solution to this differential equation is 1/3 sine of 3x minus cosine of x plus 1. My c is 1. So those are some simple differential equations, and then now you can get some practice. I think, again, this is not updated, so you're going to be looking for yours on WebAssign. I was using old notes for this. So in general, let's summarize. We have an antiderivative is a function whose derivative gives you back to the original. We have a whole infinite collection of for any given function, you have a whole infinite family of antiderivatives that all differ by a constant. We can find some antiderivatives. If we're not sure if you're right or not, you should just take the derivative of your answer and get back to the original. So that's the nice thing. We have some general antiderivatives in a table, which can be generalized slightly for if the derivative is a constant, right? So any expression when inside the function whose derivative is a constant, you can undo it. I should make note here that you can't do things like if I said my little function was f of x equals e to the x squared, the antiderivative would not be e to the x squared and then you divide by, say, 2x. So that you can only do that with a constant, because here, notice that you would need a quotient rule or a product rule or something. So it's much more complicated than that. So when I was doing my generalizations, don't generalize it more than just when the derivative is a constant. And then we have our differential equations that we can solve. All right, so good luck with homework 1.